Okay, let's dive right into today's explainer. If you're a student pilot or honestly just an aviation nerd, you've probably spent hours staring at dry textbooks, right? Memorizing V speeds, obsessing over climb profiles, only to completely blank the second your instructor tells you to take the active runway. Look, it happens to literally everyone. So today we're doing a proper pre-flight briefing. We're going to bridge that gap between ground school theory and what you actually do when you're gripping the yoke in the left seat. We're talking the physics of the climb and how mastering forces like thrust and drag will make you a significantly safer, more confident pilot. In today's explainer, we've got four main things on the agenda. First, the physics of the climb. Second, choosing your climb speed. Third, the factors that limit your performance. And finally, mastering the actual cockpit technique. So let's kick things off with Section 1, the physics of the climb, unpacking the forces. To get our foundation set, I want you to think about this question for a second. What force actually makes an airplane climb? I mean, most of us intuitively assume it's lift, right? You pull back on the yoke, the nose goes up, the wings make more lift, and boom, up you go into the clouds. But is it really just the wings hauling us into the sky? Well, actually, no. The real secret sauce here is what we call excess thrust. Think of excess thrust as your airplane's reserve bank account of power. It's the power over and above what you need just to maintain straight and level flight. If your engine can push out more power than it needs just to cruise, that spare capacity is exactly what lets you point the nose up and climb. Now drag is the tax on that bank account. The faster you go, or the dirtier your aerodynamic profile is, the more thrust goes entirely toward fighting that drag. And that leaves you with way less in reserve for your climb. So managing a climb is literally an exercise in managing your thrust and drag. And when you map out the four aerodynamic forces, you can see exactly why this happens. In a steady climb, your thrust is seriously working overtime. It's balancing the aerodynamic drag pulling you backward, sure, but it also has to balance a rearward component of your aircraft's weight that's acting straight down your upward flight path. Because thrust is taking on some of that burden of fighting gravity, the lift generated by your wings only needs to support the component of weight that's exactly perpendicular to your flight path. So we end up with this wild, almost counterintuitive reality of physics. In a steady climb, your total lift is actually slightly less than your total weight. It's that excess thrust doing the heavy lifting. Okay, now that we know excess thrust is our MVP, let's move on to Section 2, choosing your climb speed, profiles, and pitch. Up in the cockpit, we are basically always playing a game of compromises between two specific climb speeds. First, you've got best angle, or VX. Think of VX as your get-out-of-trouble speed. Like when you've got a massive 50-foot pine tree at the end of a short grass strip. It's a really steep climb used to clear obstacles over a very short horizontal distance. And it relies on having the maximum excess thrust available, which happens at lower airspeeds. Then, on the other hand, there's best rate, or VY. This is your standard, hey, let's get up to cruising altitude efficiently speed. It gives you the maximum altitude gain in the shortest amount of time, regardless of the horizontal distance you cover. VY relies on your maximum excess power. Now just look at the real-world difference between these two out the window. On the left side, in a steep VX altitude, the consequence is super obvious. Your nose completely blocks the horizon. You get that serious pucker factor of climbing out at a super steep angle, which, you need to clear those trees, but it drastically cuts your forward visibility. And that is exactly why, once we're safely clear of any obstacles, we usually transition to a faster, shallower cruise climb, like you see on the right. Dropping the nose gives you a much better view to scan for traffic. Plus, because you're flying faster, you're getting way more airflow over the cylinders, which keeps that hard-working engine from overheating. Which perfectly brings us to Section 3, factors that limit performance, attacking excess thrust. Since we know we absolutely have to protect that reserve bank account of excess thrust, what drains it? Well, we have four massive enemies of climb performance. First up is increased weight. Because gravity is actively resisting the climb, being heavy directly hurts both your rate and angle of climb. It just demands way more from your engine to stay airborne. Then we have the deadly duo, high temperatures and high altitudes. Combine these two and you get high density altitude. When the air physically thins out, your propeller just has fewer air molecules to bite into, and your engine is quite literally starved for oxygen, so it produces way less power. Finally, flap extension. Having your flaps down creates massive amounts of aerodynamic drag. And remember our rule, drag taxes your excess thrust. Dumping flaps out essentially eats right into that precious reserve we just talked about. To really put this into perspective, let's look at the hard data from a Cessna 152 POH. Take a second to scan the columns here. Notice how a hot day at a high altitude absolutely crushes your maximum rate of climb. Look at the top left.
At sea level, on a standard 0-degree day, you might be climbing comfortably at over 700 feet per minute. Not bad. Now, follow the chart all the way down to the bottom right. Push that temperature up to 40 degrees Celsius at 10,000 feet, and you're barely squeezing out 175 feet per minute. I mean, the difference is just staggering. Also, check out that recommended indicated airspeed column on the far left. See how it drops? As you climb into thinner air, fewer air molecules are entering the pitot tube, so you actually have to lower your indicated climb speed to maintain optimal aerodynamic performance.
Oh, and we definitely have to consider the invisible force outside the cockpit, the wind. Keep in mind that your airplane is climbing inside a moving parcel of air. Now, wind won't change the time it takes to reach a certain altitude. If you're climbing at 500 feet per minute, it takes 2 minutes to climb 1,000 feet, headwind or tailwind. However, a strong headwind will significantly steepen your climb angle over the ground. Because you're moving forward over the Earth more slowly while still climbing at that same vertical rate, your physical path upward is much steeper. And that is exactly why we always prefer to take off directly into the wind, because it keeps us safely above the terrain and obstacles. All right, let's bring it all together in Section 4, Master the Cockpit Technique, Execution.
So how do we actually execute all this theory with our hands on the yoke? When you're entering a climb, you want a rock-solid, repeatable habit. Always remember the acronym PAT: Power, Attitude, Trim. First, make sure your fuel mixture is rich enough to keep the engine cool, then smoothly advance that throttle to full climb power. Second, raise your attitude to the desired pitch. Now, as you raise the nose and apply all that power, the spiraling slipstream from the propeller is going to aggressively try to yaw the nose to the left. You absolutely must balance that immediately with firm right rudder. Do not forget the right rudder. And finally, once the picture out the window looks steady, trim the aircraft to take all that heavy control pressure off your hands.
Once you're established in the climb, you need to verify what your eyes are seeing outside by cross-checking your instruments. Use your airspeed indicator as your main reference to fine-tune your pitch. If you notice you're flying a bit too fast, just raise the nose slightly to bleed off some speed. If you're too slow, lower it. But whatever you do not fall into the trap of chasing the vertical speed indicator. The VSI relies on a calibrated leak, meaning it lags behind what the plane is actually doing. It basically tells you what you were doing a few seconds ago. So hold your attitude out the window, wait a second for the airspeed to settle, and keep that right leg busy on the rudder.
Now, what about when it's time to stop climbing and level off? You need a totally different sequence here so you don't just rocket right past your target altitude. A really great rule of thumb is to start your level off early, usually about 10% of your vertical speed. So if your VSI says you're climbing at 500 feet per minute, start leveling off exactly 50 feet early. We use the APPT sequence here. Adjust your attitude by gradually lowering the nose to the horizon. Then pause. This pause is absolutely critical. Leave your climb power set and let the airplane accelerate horizontally to its cruise speed. Once you hit that faster cruise speed, pull back your power to your normal cruise setting. And lastly, trim out those new control pressures so you can fly hands off. So, as we wrap up today's explainer, I want to leave you with a crucial question to chew on before your next flight. How are you going to manage your excess thrust? The next time you push that throttle forward and ease back on the yoke, just remember that it's not some aerodynamic magic pulling you up into the clouds. It is a really precise, delicate balance. You're managing density altitude, calculating your weight, and maintaining precise pitch control to protect that critical reserve bank account of thrust. So respect the drag, kneel your airspeeds, keep that right rudder pressed firmly to the floor, and enjoy the climb. Thanks so much for joining me for this explainer, and I'll catch you on the next one.